Hello everyone. Today we're looking at Unit 1, Lesson 4, Substitution and Elimination Continued. So we've spent the past few lessons discussing different algebraic methods to solve linear systems. Today we're really going to take a look at how do we know which method we should use depending on the linear system that's presented to us. So before we get into how do you know which method to use, let's go ahead and try to solve this linear system we have here using elimination. Okay, so we're going to use elimination. And this will kind of lead us into what we're doing today. But notice that the reason I would choose to use elimination for this one is because we have our x term, and it's right above the x term in the other equation. We have our y term over our y term, and we have our constant over our constant. Okay, so when we have them all lined up with that, we should be thinking in our head right away, elimination. I'm going to erase the highlighter for now. But the first step in elimination is that we're going to label our equations 1 and 2. All right, now before we worry about whether or not we need to multiply to get the same magnitude, we looked at this in our review. We need to clear the fraction. So we have these fractions happening here. We need to clear the fraction so that we're working with whole numbers, and it just makes life a whole lot easier. Let's actually, I'm going to move our number of equations over here. So if I think about equation 1, in order to clear the fraction, I need to multiply by the lowest common denominator. So in this case, we're going to multiply by 6 to clear the fraction. And on equation 2, I have a denominator of 6 and 5. So my lowest common denominator, or multiple, is going to be 30 here. So let's multiply everything through by 6 and see where that gets us. So I'm going to do x over 3, and I'm going to multiply this by 6. I'm going to do y over 2 and multiply that by 6. And then finally I'm going to do a negative 3 times 6. All right, and from there, we should do some simplifying. We should see that the 6 and the 3 will just reduce to a 2, so we'll have 2x. The 6 and the 2 on our y is going to reduce to a 3, so we're going to have 3y, and that's going to equal a negative 18. And we're just going to write equation 1 next to that again, so we remember that's our newly transformed equation 1. Okay, for equation 2, I'm going to take x over 6, and again I'm going to multiply by 30, and do my y over 5 and multiply by 30, and then finally we'll do 3 times 30. Okay, so when we multiply 30 times x over 6, that 30 and the 6 is going to reduce to 5. So we'll have 5x plus the 30 and the 5 on our y is going to reduce to 6. So we'll have 6y, and then 3 times 30 is 90. So that is equation 2. Now we haven't even gotten to actually, can we eliminate anything now? Have to figure out, do I need to multiply either of these equations by something to be able to eliminate? So if we look at our x's, we see that we have a 2 and a 5. So I would have to multiply both equations by something to get those magnitudes the same. But if I look at my y values, I have a negative 3 on this y, and I have a positive 6 on this y. So could I multiply an equation by something to get that same number? And the answer is yes. I could multiply equation 1 by 2, and that's going to change my negative 3 to a negative 6, so then I'll have the same magnitude. So we're just going to kind of move down here because we've run out of room. So we'll multiply everything in equation 1 by 2. So we're going to get 4x minus 6y equals a negative 36. Okay, we're not going to do anything to equation 2. We're just going to bring it down to the next line. So we'll have 5x plus 6y equals 90. Okay, and now since they have the same magnitude, but they have the opposite sign, we are going to add equation 1 and 2, And it's always good to, again, communicate that. So we're going to do 1 plus equation 2 in order to eliminate our y's. So we have 4x plus 5x. That's going to get us 9x. My y's are going to drop away because I have a negative 6y plus positive 6y. And then a negative 36. Oh, this should be a 36, not a 30. Sorry about that. Negative 18 times 2 is a negative 36. So I have a negative 36 plus 90 is going to be 54. And then we'll just work to isolate x. So we're going to divide by 9, and we're going to get that x is equal to 6. And now we're going to take 6 and we're going to substitute it into one of our equations. I'm going to substitute it into equation 1 just because the numbers are a bit smaller. So I'm going to sub x equals 6 into equation 1. And I'm going to substitute it into equation 1 where we had gotten rid of the fractions, because again, that'll be easier to work with. So let's just write equation 1 in blue. So my equation 1 is 2, and then I'm going to put brackets where I'm going to fill in what I'm substituting in. Minus 3y equals a negative 18. And then we'll just work to simplify. So we'll have 12 minus 3y equals negative 18. I'm going to bring that 12 over by subtracting. So we're going to end up with a negative 30. And then finally, we'll divide both sides by negative 3. So y will equal 10. Okay? And then the last step, okay, we substituted into equation 1. So we're going to need to check it now in equation 2. So check in 2. So we will do a left side, right side check using my simplified equation 2 as well. So after we cleared the fraction, the left side of equation 2 was 5x plus 6y, and the right side was just 90. So we'll substitute in our values. For x, we'll sub in a 6, and for y, we'll substitute in 10. Now 5 times 6 is 30, 6 times 10 is 60. So you get 90, which is exactly what we have on the right side there. So our left side equals our right side. So we can say, therefore, the solution is 6, 10. Right? So that's just going through the elimination process again, but working with the idea if we have a fraction, we need to clear that fraction to work more easily with those equations and those systems. All right, but how do you know when to use each method? How do you know if we should use substitution or if we should use elimination? And the key there is kind of in the names of the methods. So with substitution, we want to make sure that there's a variable isolated, or that it's like really easy to isolate a variable based on the equations that have been given to us. Because once a variable is isolated, we can just substitute in what that variable is equal to into the other equation, and we're moving along with the substitution method. So we want to use substitution if a variable is already isolated or it's easy to do so. Okay, so if it's easy to get that variable isolated or it's already isolated for you, we're going to use substitution. For elimination, if the variables are lined up over each other, or again, it's easy to do so, then we want to use elimination. So in today's note, really what we're going to do is I'm going to go through a couple examples with you, and then I'm going to get you guys to go through a couple of examples. A couple of them I might just help you get started in case there's some parts that might be tripping you up, but it's going to be more I try, you try for the rest of the note today. All right, so let's take a look. So let's take a look at some examples and see if we can determine which method is the best method for solving these linear systems. So our first example here, we have our equation 1 and we have our equation 2, okay? And we can see that equation 1 is solved for y. So whenever we have one of our equations solved for y, we're going to go ahead and use substitution. So we're going to, therefore, would use substitution. Right, since it's already rearranged, we would take that equation 1 and we're going to sub 1 into 2. Right, let's take a look at our next example. So our next example, if we were thinking about substitution, we would need to isolate for x or y, but both my x's and y's have coefficients on them, so it wouldn't be overly easy to rearrange and solve for x or y, so we should start thinking elimination. So if we were trying to get the coefficient on our y the same, let's say again this is our equation 1, this is our equation 2. Right now our y's have a 2 and a 3 on them. So if we want to get the coefficient the same on them, our lowest common multiple would be 6. So I could multiply equation 1 by 3, and I could multiply equation 2 by 2, because 3 times 2 will be 6. So this is how we'd go about eliminating the y's. Or maybe we decide we want to eliminate the x's. If we want to eliminate the x's, we have to take a look at what do we have for our x's. So on our x's, we have a 5x and a 4x. So our our lowest common multiple would be 20. So to get equation 1 to 20, I'd have to multiply that by 4. And my second equation, since I have a 4x, I'd have to multiply that by 5. And then they would both be at 20, and we could work to eliminate the x's. Go ahead and look at that next example. So if we look at our next example, we have our x's and our y's lined up over each other. Hopefully you can see here, right? We have our x's right over each other. So when that's the case, we can easily eliminate the x's using elimination. So if we think about this as equation 1, equation 2, remember since they are the same side, we're going to subtract them. So we would do equation 1 minus equation 2. All right, but something else to kind of take note of is that we have this y all by itself. So if we have y by itself, it would be really easy to isolate for y. So maybe we want to isolate for y, because maybe we're a person that prefers to use substitution. So if we were to isolate for y, we would go ahead and use substitution. So this example kind of lends itself to do either. So we could say substitution or elimination really works in this example. Take a look at that next one. We have 1.2x plus 2.4y. So we will again call these our equation 1, equation 2. And again, now we have our y's stacked over each other. So when we have our y's stacked over each other, we can do 1 minus 2. Okay, so it would be really easy to eliminate y. And I just want to make a little side note here because we've seen 2 examples of elimination now. So let's just make a note here so that we remember when we're eliminating, how do we know if we add or subtract? So just make a side note here. So if it's the same sign, we subtract the equations. If it's opposite signs, we add the equations. So you can see on this example here, right, they had the same side. So if we were trying to eliminate our y, we have a positive 2.4 and we have a positive 2.4. So they have the same sign, which means we are going to subtract them because 2.4 minus 2.4 will be 0. Let's take a look at a few more. Okay, so our next example here, we have some fractions to deal with, but we can deal with that no matter if we choose to use substitution or elimination. So let's call this equation 1, equation 2. You can see that y has been isolated for in both equations. So we could sub 1 into 2 or 2 into 1, both isolated. So we're going to use substitution. And we can say we'll sub 1 into 2. Or 2 into 1, either way, right? So we could say if we were subbing 1 into 2, we would be taking our equation 2, we'd put a bracket anywhere we see a y. It's going to be equal to 3/4 x minus 10. And in place of my y, I'm going to substitute that equation 1. And then we work to get rid of fraction and so on. Okay, we clear our fraction and then we use just algebra to solve for x. All right, let's take a look at just a couple more. So on this next example, we have lots of fractions to deal with. So let's label our equations 1 and 2. Okay, and we can see that we have x and y isolated here. So they'd be easy to isolate. X and y would be easy to isolate. But would need to clear the fraction still. So since those fractions are going to be an issue, you might end up with a coefficient on those x's and y when you go to clear them. So since we already have our x's lined up over our x's and our y's over our y's, elimination might be a better choice. And with any of these, you can use either elimination, might be a better choice. You could use elimination or substitution. It's just which one is kind of most efficient for where the problem is at. So elimination might be a better choice and deal with the fractions right off at the beginning, and then you can deal with if your x's and y's are lined up, what can be eliminated. Okay, so just something to kind of think about there. This next one, again, we have lots of fractions that we're dealing with, but we can see that y would be easy to isolate. I know that we have some fractions in our first one, but we only need to isolate for one equation. So since we could easily isolate for y, then substitute. Again, the point here is that substitution or elimination will always work. It's just a matter of which one are you more comfortable with, for one, and which one's kind of more efficient. So if on one of these problems I said, oh, you should use substitution, it doesn't mean you can't use elimination. It just means the way it's set up that substitution or elimination would lend itself to the least amount of steps. So I'll just put here, even though I said isolate for y, then substitute, not the. I'm going to put or elimination. Because it comes down to your choice, right? What's your preference? What are you more comfortable using? As long as you can apply the steps to substitution or elimination, then either is going to work out fine, okay? Hopefully in our next day's lesson, I'm hoping to actually solve these linear systems with you.